Hello guys, my name is Jeferson Costa, I'm a chemical process engineer, and today I'm here to record a video to celebrate the 1000 subscribers to my channel. And to do that, I will evaluate a Mentee process simulation done in Aspen HYSYS. And before I start, I would like to invite you to know my other social media like YouTube, Telegram, and LinkedIn. And just to let you know, in Telegram you have exclusive content and other videos and audios that I do there and share with people. So this is the process simulation that he did, and I don't have the process description about it, but we can verify what is happening here, okay? So we get a stream of condensate feed. It should be with hydrocarbon. You can confirm that in the composition, and it is mixed with water and preheated before entering a storage vessel. And we have a three-phase separator vessel. So in the bottom we expected to have water, and we can see that in the composition. Here we have the water, and we have a stream with hydrocarbon, a liquid stream with hydrocarbon, and a gas stream with hydrocarbon also. How do you identify if it is liquid or if it is gas? It is very easy. See that in the C104 the vapor phase fraction is 0, so it means that it is a liquid phase. And in the C103 you can see that vapor phase fraction is 1, so it is gas saturated, and we have liquid saturated also. And the main purpose of the heat exchanger is to partially vaporize or add heating to the liquid stream in order that it is easier to separate the liquid from the gas. Once we have the gas, it goes to the compressor suction, and we have a recovery of this liquid, and so we have a split of this liquid and a preheating of it before entering the absorber, and a source of heat to add heat to this in order that the liquid can vaporize and goes to the compressor suction. So in the bottom we have our waste, and it is hot. You can see that it is 155 Celsius degrees, and because of that he used a heat exchanger to preheat the liquid from 38 degrees Celsius to 60 degrees Celsius, and the return in the waste he used it also to do the pre-heating of the raw material at the plant inlet or at the battery limit. And as this condensate, we can confirm that verifying the vapor phase is 0. So as this condensate is too hot, he added an air cooler to cool down that, and in this way you can send that for the waste treatment. And talking about the gas, it goes to a compressor. When we represent this kind of arrangement, it means that it is a compressor, a three-stage compressor, and we have aftercooler in the discharge of each stage to cool down the gas and prevent the equipment damage. So in this case we have here from 40 to 30 degrees Celsius, and we have some condensates here because these streams, as you remember, it is saturated, and once we compress again, build pressure and refrigerate, and in the final stage it was not considered after cooler, and he asked me to verify why the heat exchanger, this one E102, was not converging. And the first thing that I can tell you is that the Aspen HYSYS or chemical process simulation sometimes accept everything that you tell him, and you need to have a critical evaluation of your process simulation to verify that it is feasible, if it makes sense. And my point of view here is from a guy that works with plan design. I'm not a scientist and I'm not a teacher, okay? So I will do some comments related to this process simulation based on if I were evaluating that for a plan design. So it means that we need to do process flow diagram, piping instrumentation diagram, process datasheet for equipment, process datasheet for instrumentations, and moreover, if you don't know what a chemical process engineer does in a design office, you can see the video that I share with you in YouTube. You may see a remark here right now. So let's start the evaluation. The first thing that I will do to start the evaluation is to add some information in the screen for me, make it easier to understand what's happening, and fix also or adjust the units, engineering units, in a way that I'm used to have in my work. So for instance, here I can show the table for this stream, clicking with the right button of my mouse, and I can have the information of temperature, pressure, and molar flow. I can see the same in the stream C112. So I click with the right side of the mouse and I choose show table, and we have a standard information with pressure, temperature, and molar flow. We can adjust that. We can set another set of information, but right now it's okay for me. And what takes my attention now is that usually we don't use kilopascal as a measurement for pressure in real life. Normally the process in real life operates at a very high pressure. It can be 2 bar, 10 bar. I have seen up to 200 bars, and kilopascal is a very low measurement. I will set another pressure unit for pressure. To do that, I can go in home and click in unit set. I will do a new set for me, units. Once you do that, is saved in the Aspen HYSYS memory. And now that I have units, I can change the unit I want to a variable. So in this case, I want pressure as bar, and depending on your company, I have seen also the use of kilogram per centimeter square. And if you are in an American company, most often you use PSA. In this case, I will use bar. And another measurement that I will change is the molar flow, because we don't measure the flows in kilomole per hour. Most often, if we are handling gas, we use normal cubic meter per hour or standard cubic meter per hour or per minute. And if we are handling liquid, we use cubic meter or something related to that. In this case, I will change kilomole to normal cubic meter per hour. And now I can start doing some conclusion. And we have here a mix of hydrocarbons, with almost 15 degrees Celsius at 90.5 bar and molar flow of 1629 normal cubic meter per hour, and it is heated up to 39 Celsius, and we have also some pressure drop, and because of that and after preheating the liquid goes to the process. And when there is something not right or something wrong or something strange in the simulation, the Aspen HYSYS gives you some information that something is not going good. So when I double click in the heat exchanger, it informs me that it is over specified. And it is over specified because we can see here in the worksheet, mixed stream that is going into the heat exchanger is full specified, and the stream that goes out from the heat exchanger has its temperature set. You need to remember that heat flow is equal MC delta T. So I have the mass, I have Cp from the stream, and if I have the downstream temperature and the upstream temperature, I have set the heat flow. On the other hand, it was done the same in the waste stream. You can see that we have the H111. We have also the mass flow, we have the inlet temperature, and we have the downstream temperature also. And it means this heat exchanger is oversized because it is calculating heat flow 2 times. And once we already have the heat flow from this stream, the heat flow calculated will define the temperature outlet of the waste stream. If you don't get it, I will just do it in separated equipment to you visualize better what I am talking about. The heat exchanger, in fact, is a combination of two processes or two process units. It is the process of heating a stream, and in the other hand, the process of cooling another stream. To show you that, I will use the model palette and I will simulate the heating and I will simulate the cooling, and we will verify if the heat transfer is the same. It needs to be the same to the heat exchanger convert. So first I will simulate the heating. I choose heat and double clicking I open the design table. So here I have set the connections to the heat exchanger, and now I will define the inlet based in the existing stream, that is C-101A, this one, the same. Nice, now we have the interest defined, and I will do now two things. First, before converting the equipment, we need to inform the delta P. I'll use the same that we have in this one. And the delta P we find at the design tab and parameters. So we have here the shell side with 13.79 kilopascal. I will change that, and the tube side also. And how do I know what is each thing? You can see that we have a line here crossing the heat exchanger. It represents the tube side of the heat exchanger, and this one that enters the bounds of the heat exchanger, it represents the shell. And so in this case I have the mixed gas going in the tube, and I will copy that and use in the the other equipment. So in this case I have pressure drop here, and I will paste. So I have the let string specification, I have the delta P, the dut is unknown because I want to calculate that, and now I will define the outlet temperature, and once I do that, the Aspen HYSYS will calculate the heat needed to heat this stream. So in this case we use the same temperature, and we have here 39 degrees Celsius. You can see that this bar is on green, so it means that it converted very well. Now I show a table to verify the heat flow is here. And now I will compare the heat flow with the cooling down side. And to do that, we use the unit cooler, and I'll do a process very similar to what we've done to the heating. Now I need to define the inlet stream that is based in H111, and to do that we go in define front stream, and okay, we have the definition, inlet stream, we have pressure drop, and to define the heat flow, we only need to inform the outside temperature. And in this case, outside temperature is 93.33. 93.33 Celsius. You can see that the heat exchanger converted, and now we need to verify if the heat flow is the same for both of them, because if it is not the same, there is an inconsistency and the Aspen HYSYS will not convert well. And we can see that the heat flow to heat the stream, the liquid stream or mixed stream, is much higher than the heat flow needed to cool down the H111 stream from 144 Celsius to 93 Celsius. And that's why we have inconsistency here, and this is why the equipment did not convert well. And now let's do some critical evaluation. The first thing, the heat transfer is based on mass flow and based on also in delta T. And we have a mass flow of this stream much lesser than the other stream. So it would be a clue to verify that something is not right here, because how can I heat up a stream of 2,600 kilograms per hour with a stream with only 161? Okay, so this is the first thing that I evaluate in this process simulation and verify that something is wrong. And other thing that I verified was, instead of defining the outlet temperature, was defining the heat flow and see which outside temperature the Aspen HYSYS would calculate for me. And when I use this stream to cool down the waste condensate, the Aspen HYSYS is not able to calculate the outlet temperature. So this means that it is too much heat flow to this stream to handle. But you should be asking yourself, if it's not feasible, why Aspen HYSYS converted the simulation take in consideration overview of the process. It is because we have this stream defined. We have the inlet stream, we have the outlet stream, we have the inlet pressure, the inlet temperature and outlet temperature. We have flow, and because of that we have specified the stream to the three-phase separator and goes on. If I disconnect the stream H111 from the heat exchanger for the process simulation, it will keep running the simulation, because as I told you, the inlet stream in the separator vessel is already defined, and the only stream that will not have the specification is the condensate stream, because now we don't have the connection. On the other hand, if I reconnect the H stream and if I change the outlet temperature, there is a value that do not convert more the other streams. Let's see, for instance, if I change from 39 to 30, and if I change 30 to 20, and if I change 20 to 15, the 15 temperature is too low to convert the simulation. And if I return to 20, don't do the calculation, because when there is an error, it was putting on hold, and now if I do activate, it calculates everything again, and now I have process simulation converted. It would not be the best conversion, taking into consideration the process in itself, but the calculation is responding. And now, considering that we want to preheat the stream and that we need at least 39 degrees Celsius to enter the vessel separator, we can do some things here. The first thing is that I will add another heater in series with the preheater. So in this case, I will use the heater unit, and okay, now I just need to inform the outlet temperature to convert the equipment, and as we have seen before, we need at least 39 Celsius. And another thing that I need to inform is the heat stream. So, but it is calculated, and now what I will do in the preheat is decrease the temperature up to have a feasible temperature in the outlet stream. First of all, let's delete that because we don't need this. And now we can solve that decreasing the outlet temperature, and now you see that the equipment converted because the hot side and the cold side has the same flow, the same heat flow. This is an option that we can do, but would be others also for sure, and it's a matter of economics to evaluate if the better solution is adding, for instance, electrical heater here to heat this stream. And now, although the simulation converted, and in a point of taking into account only the process simulation, it was done, it would complete, no problem. I have verified some issues also in the compressor system, and I will talk to you about that now. The table resource or the table feature is very useful when you want to verify the information and don't want to double clicking in the stream, because once you change something it automatically shows to you. And here I have the compressor, and you can see in this case something that does not make sense also in a real case, okay, because I have at the inlet pressure at the compressor is above the outside pressure of the compressor. It does make any sense in a real process, and it is because we have a cooler here that was defined with pressure drop too high, and we have here around 6 bar of pressure drop in this equipment. It doesn't make any sense, and usually what we have is we have a pressure rate for each stage of the equipment of the compressor. So in this case we see here in design, and the pressure rate is 1. It is too low. I don't have the numbers right now, and let's consider for each stage at least 2 times pressure rate. And there is a limit for pressure rate, because once you compress too much the gas, its temperature goes up, and to not damage the equipment, the suppliers and the manufacturers calculates the outlet temperature that it goes around 150 or something like that, to prevent the material that I used. And it would be a resource for our preheating recovery, because we could use instead of using the air cooler to cool down the compressor discharge, we would recirculate that to the preheating, and in that case save some energy in the electrical heater. Maybe you are not getting what I'm talking about, so just verify what I will do. Instead of using an electrical heater, and the electrical heater E106, and instead of cooling down the compressor discharge with air cooler, I will use the cross heat exchanger to preheat the inlet stream and to cool down the compressor discharge. I'll do that first. Break this, okay, as the stream is defined, no problem. And I will break this also. And now I will take the discharge of the compressor, and I will use this as the inlet. I use this at the inlet of the shell side. And the return, I will do the same. So the return will be, let's just verify, I will delete this temperature, because as you have seen, we already have the heat flow defined in that heat exchanger, and once I connect the C212 there, we will see what is the temperature that will going out from the equipment. And in this case, you connect that, and you can see that it converted. And now let's see the outlet of the compressor going out as 74 Celsius and returning with 70, so I have some space for heat exchanging. Let's verify now if it's possible to remove the electrical heater, increasing the outlet temperature of the preheater. And to follow that, let's see the return temperature. So now we have use 20, and you can see that the heat exchanger for the electrical heater, the heat flow is decreasing. It means that I could use less power to run this plant in this case, but I want more. So the temperature, returning temperature is decreasing, and the heat exchanger and the electrical heater power is decreasing also. And as I want 39, you must observe we don't only evaluate the capture expenditure, that it is the money that you need to build your plant, but also the operation expenditure, that is the money that you expend to run your plant. I won't do that kind of calculation, but for now we will consider that 32 is enough to have a more economical process. So in this case I can have two things here. Because to start the plant, I need to have this stream at the desired temperature I want. So instead, in the normal operation, I will have the electrical heat off. During startup, I need to heat the stream because I don't have a compressor running, and I will change this stream like this. I will not define the outlet temperature, but I will define the heat will be 0. And this way, in normal operation, I don't need the electrical heater, but during startup I need that because I need to have around 32 to 39 degrees Celsius to have a good to be able to run my stabilizer. Okay, and to finish that, the last stream that we will handle is the condensate that is very hot, and we will connect that to the air cooler. Connections. And we'll connect that to air cooler. And once we connect that, we'll have the condensate at the desired temperature to the stream, to the waste treatment. And with that, we could save one equipment. If we cannot save the after cooler at the compressor discharge, at least the plant operational expenditure will be lower, because instead of using an electrical heater to heat the stream to the three-phase separator, we will be using the discharge temperature of the first stage compression. And with that, my friends, I finished the evaluation of the simulation. Of course, there are a lot of chemical process engineering documentation to be done to make it real. And if you are interested in downloading this simulation, the original simulation that was shared with me. It's very easy. First you need to be an in-process member, and to be an in-process member you just need to go to my website jeffersoncosta.com, just one F, and look for Telegram or in-process tab. And once you are in the in-process tab, you will see a short description about my in-process Telegram channel, and just click in the button get inside the group for free, and you will be able to download the simulation if and only if we reach at least 100 likes in this video. So if you want to download it, if you want to have more videos in this channel, and if you want to help me getting more and more chemical process engineer connected together, you just need to share this video with many people. My name is Jeferson Costa, I'm a chemical process engineer, and now we're going to reach 2,000 subscribers soon. Bye bye my friends.